Hi, I'm Matt, a founder of Explosion AI and the author of spaCy, a popular library for creating advanced natural understanding systems. In this video, I'm going to show you how to create a new phrase classification system, and we're going to start from the beginning, creating the training and evaluation data that the statistical model will learn from. And we're going to end up with a system that can be easily deployed to production. I wanted to make this video because creating new capabilities is really the exciting part about artificial intelligence technologies, and yet is completely left out of most AI tutorials. Most AI tutorials are all about working with existing data sets. If you start out with a bunch of images categorized into buckets like breed of dog or whatever, you can make a model that sorts the images into exactly those buckets. But identifying breed of dogs is just a demo. It just shows you what's possible. But in order to cache that possibility in, we have to create new data. And that's exactly what our new annotation tool Prodigy lets you do. So, what capabilities should we create? For this example, I thought it would be interesting to look at text from one of the largest online communities of US opiate users. Millions of words of conversation from this community are publicly available, going back a number of years. This seems like a good resource for investigating questions about the emergence and progress of the opioid crisis. To make use of this text, we need to be able to process it in intelligent ways. It's not enough to look at shallow features, such as the frequency of individual words over time. Terms change, and so does the online community. If we look only at the frequency of one term, such as fentanyl, we have no way of knowing whether we're seeing a reflection of something important or just an artifact in the data. Instead of manually picking out keywords, we'll train a model to systematically tag all references of drugs. This way, we can look at relative frequencies instead of just saying, okay, this word fentanyl increases in frequency. We can group it together with its synonyms and look for whether it takes up a greater percentage of drug references over time. So, here's an example of the output of the model after just 1 hour of annotation and training. As you can see, it's not perfect, but it's still a great start. While it's still missing some terms and identifying some false positives, the knowledge it already has can be used as part of the further training process using Prodigy's active learning technology. In order to create our phrase classification model, we're going to start with a terminology list, and we're going to build this terminology list interactively using spaCy's inbuilt word vectors, which are trained on billions of words of text from the web. So the first step of this is to start creating a data set to hold our term annotations, because we're going to build this data set interactively. So we start out by running this command, Prodigy dataset, to hold the terms that we're going to annotate. And we created a description here, seed terms, that allows us to easily refer to this later. So now we'll start the terms classification service. So we're going to run this recipe function, prodigy terms.teach, with the data set that we created before, and the EN-core WebLG spaCy model, which includes the large glove vectors trained by researchers from Stanford. We'll also start with these seed terms, heroin, benzos, and weed, to give the model some sense of the sort of terms that we're interested in. These terms will be used to create a sort of, will be averaged together to create a sort of vector representation of the meaning that we're interested in. The prodigy terms.teach command starts a web server. So this gives us an address that we can then visit with our web browser to start the annotation session. So after loading up the site, we see this, the annotation interface. We have here the first question that we're asked to annotate, and we have these buttons. We can click the green accept, or we can say the red no. The red no means that the term is not a term which we want to add to our lexicon. It's not a term that's going to be a drug term. Or in fact, we could ignore, and we can also undo. So the undo is particularly handy if we start going quickly, and then if we make a mistake, we can just go back a couple and fix the error. We also get an indication of the progress and a count of the number of terms that we've accepted and rejected. So let's start clicking through this. So in this case, for opiates, we click yes. For cocaine, that's a term, drug term, yes. Narcotic, no. That's more of a general term. Methadone, yes. Drugs, no. Narcotics. We can also use the keys and just say A, and X. So here we can start going a little bit quicker and just start basically getting into a rhythm of clicking through these. Many of these are actually spelling mistakes which I wouldn't have anticipated, and that's where the word vectors are particularly handy, because the misspellings tend to have pretty much exactly the same distribution or usage pattern as the main term, and this makes them easy to identify for the word vectors. We see here a rejection of a lot of terms which are associated with drug use but are not themselves drugs, and so you can see how this is sort of sharpening up and starting to zoom in on the types of words that we're interested in. So we continue annotating. Some of these terms are a little bit borderline, but you know, the main thing is to basically start building up a pretty wide set of these terms. And it's okay if the terms are ambiguous as well, such as Coke, because later we're going to annotate these in context as well as just have the word list. So let's see. Tylenol, even though this is a non-narcotic drug, we'll consider it part of the same thing. It's still there as a drug. Otherwise, we have to decide what type of drug people are getting high with, and this becomes too difficult a policy. So we'll just have it simply as, you know, is it a drug substance or not? Okay, so cannabinoids, well, we'll say it's a chemical substance. Maybe that's borderline as well. Maybe that's a drug term of the future. Iban. Some of these, we could really play Pokemon or narcotic, and you know, we could look these up, but it's actually more useful a lot of the time to just keep moving, because there tends to be more of these than we have patience to annotate anyway, and so it's more efficient to just kind of keep moving through them instead of stopping and looking up everything in Wikipedia. The interface can actually be extended to show information from Wikipedia alongside these things as well, if that's you know, decisive. For instance, it's very easy to show the first sentence of Wikipedia alongside the interface. Some of these misspellings are quite creative. Definitely not things that I would have come up with myself if I were trying to come up with misspellings of things. This is another Pokemon. No, narcotic. Wait, yeah, narcotic. Maybe. So now that you've got a sense of the process, you know, even though this was really only 10 minutes of annotation work, to get this term list, we'll speed this up slightly just to avoid you sitting through those 10 minutes, which, you know, tend to be rather samey. So at the end of that short annotation session, we have a terminology list of 118 terms that refer to different drugs. And this terminology list includes a lot of terms which we couldn't easily have gotten from an existing knowledge base, and certainly things which we wouldn't have guessed ourselves. Things like misspellings or slang terms, and you know, including a wide variety of these substances. And we got this terminology list after only 300 clicks. So you can see that even if at a pretty leisurely pace of, say, 2 or 3 seconds per click, this is still only taking a couple of minutes. So this is easily something that you can do yourself. You don't need to have a number of different annotators helping you, or you don't need to get anybody else involved. You can just do this. And that's really something that's at the heart of what we're trying to do with Prodigy. We want to make sure that the annotation process is sufficient enough that when you have an idea, you can basically just try it out. You don't have to convene a meeting and start lobbying for resources to try out your plan. You can just do things. And I think that really matches up well with the rest of the data science workflow and really adds this missing piece. Because otherwise, you really end up in this sort of waterfall process of planning out the project in ways which you really can't back up, because it's too hard to guess these things. So I think having that sort of self-process is a lot better. So, okay. So in order to make that happen, we need the annotation to be as efficient as possible. And the key to that sort of efficiency, as we saw in the terminology list, is to have this sort of binary interface, to have the model doing as much of the work as possible, and you really just have to click through yes or no. Now, for some tasks like the terminology list, this is pretty easy, right? Like it's sort of inherently a binary task. But for other tasks, such as named entity recognition, which is a structured prediction problem, we have to do a little bit more work. But fortunately, there's lots of different ways to solve these machine learning problems and lots of different ways to structure the model. And so we can start sort of reaching deeper into this bag of tricks to make this happen. And it turns out that, it does take a little bit of work, but, it's not so arduous. And there's certainly no shortage of research on these questions. So this is where the active learning comes in, and also some other bootstrapping techniques. So, and this is also one of the reasons why the terminology list was so important in the first place. It's really what sort of gets us to get started in this bootstrapping process, because we can use the terminology list to drive the entity recognizer forward and get it over that cold start process. So the terminology list will really be the process by which we start suggesting these terms in context. And that'll give us something to say yes or no to, and that'll let the model's engine sort of get started. So in order to make that happen, we have a little utility function here, which we say Prodigy terms.toPatterns. And this is going to convert the terminology list into a patterns file that we can feed into spaCy's matcher class. And this will allow us to create our rule-based entity recognition system. So we see here the JSON-L formatted pattern file. Incidentally, pretty much everything is in this sort of easy to use format in Prodigy. It's stored by default in an SQLite database, but you can easily export these things and basically start processing them in whatever text format that you like. So the patterns file by default here is very simple. It's just one lowercase term, so it's just going to match that term and assign it to the drug label. But spaCy's matcher class supports all sorts of other properties and tokens. So we could, for instance, have a pattern which says a noun before some word and then making a multi-word phrase, or making a multi-word phrase based on other properties such as other annotations which spaCy calculates. So we really have a pretty flexible way of writing these rules that allows the bootstrapping to get started. So we're going to use this matcher class to start suggesting the rules, and this will give us something to say yes or no to, and then this will allow the statistical model to start learning this as well. So in order to get started with this, we create our data set, and then we run the Prodigy ner.teach command, saving the data under this drug's NER label that we just created, and starting the model off with the Ian Core WebLG spaCy model, which is trained on the OntoNotes corpus and also starts with the word vectors that we had before. So after starting the server, we can then switch over to the web browser and start looking through these things and start clicking yes or no to things. So as before, we have the same yes or no interface. So we start clicking through these. We say Xanax, yes. Cocaine, yes. Coke, in this case, yes. This also, some of these are ambiguous, but we can either take a guess or ignore them. Put in a glass of Coke as an example of a reject, because this is plainly the beverage Coca-Cola. The model here is we start off with these examples, which are basically all generated by the patterns, but the statistical model also has the opportunity to start suggesting things. And as it does so, we're going to be start getting asked these questions of phrases that the model has suggested. And that gives the model an opportunity to learn the patterns that of what is and is not a drug reference. And so over time, the idea is that we start off with these fixed set of patterns, but the statistical model gets to learn these in context and gets to suggest other similar words based on these contextual patterns using its neural network model. The model does a few things here to cut down the amount of work that you have to do and to make that work as quick as possible for you. So one of the things it does is it processes a batch of text and tries to ask you to set questions about the same word in a row, so that if it's going to ask you questions about, say, 5 questions about, say, a single word, then those questions will all be grouped together, because then they'll be easier to make. It also groups together questions. It also resorts the questions so that it's asking questions that it's least sure about. So it's trying to find questions where the score is as close to 0.5 as possible. In machine learning, this is called uncertainty sampling in active learning. And this simple strategy actually works very well at making sure that you don't have to answer all of these questions which the model already gets right. So it's focusing its attention on questions which it's already likely to get wrong either way, so that the annotations are more useful. This means that overall the annotation process is very quick. So you need to make fewer decisions, and the decisions that you do make can be made as quickly as possible. So speeding this up a little bit, we can see that the annotation process, which we're going to target, say, 600 annotations here, can really be done in just a few minutes. So I think for this process we took maybe 15 to 30 minutes to make these 600 decisions while we were discussing some of them as well. For some more details about the model, we've prepared a video that describes spaCy's named entity recognition model. The underlying machine learning technology here in spaCy is open source, so you can view how this works, and updates to it will be released, and you can sort of make your own patches to it as well. You can also plug in your own named entity recognition technologies. Really all that you have to do is have a model which can be updated from the annotations, and that is able to produce scores of the examples as the stream is processed. So in the case of the model which we use in spaCy, we update from the partial annotations here using beam search. So we parse the sentence twice, one without any knowledge of the constraints that we apply with these annotations, and a second one constrained so that the parse that's produced, the whole entity analysis over the text, is consistent with what you've said with the entities that you've accepted or rejected. So we get the best scoring analysis that doesn't have any mistakes according to the annotations that you make. And then we use that best scoring analysis as the gold standard. So we update the model so that parsers which are in that set of best scoring analyses are produced more frequently or with higher scores. Even though this doesn't give the model perfect information over the data which is being annotated, this still allows it to converge, because it still gets to say, okay, this is a mistake that I made, this is something which I assigned some score to, and now I know that's not correct. Or alternatively, you can say, this entity is correct, and so I must produce only parsers which include that entity within it. So long as you can produce a model which is updated in this sort of way, then you can easily plug your own named entity recognition technology in. So you can train a model with TensorFlow or some other, or PyTorch or however else. Alternatively, you can also use one of those frameworks to plug an entity recognition model into spaCy. So these technologies are all kind of pluggable and hackable. Another thing that you can do is write your own recipe for these things. So even using spaCy's entity recognition model, you can resort the stream in some other way that's useful to you. So another way that can work well is to simply take the most frequent entities in some quite large batch of text. And then you can say, all right, I'm going to take all of the occurrences of this and just sort of go through those very quickly. And this means that you might be able to do thousands of these annotations very quickly, because the answer might all be yes for some phrase. But you can confirm all of those and move through them super quick, and then you get those annotations. So there are actually quite a lot of ways that you can sort of mix and match these things and write your own little recipe functions. All that you have to do is return a dictionary that gives the stream of examples, and optionally an update callback so that the model can learn in the loop like this. So we really tried to build Prodigy on these open technologies and sort of open hackable philosophy, because we think that this is a tool for people who are doing things and people who can program, and so we didn't want to constrain your choices and pretend that we knew everything about what you were doing or had all of the answers ahead of time. there's plenty of opportunity to plug your own things into it and sort of customize it to whatever other problems that you're working on. Another thing that you can customize here is the progress bar. So by default, the progress that's calculated, it's trying to do a simple regression towards to predict when the loss will hit 0. So a loss is returned from the model on each update, and so we just have a simple calculation trying to determine at which number of example the loss will trend towards 0. But you can plug in your own calculation here. So ahead of time, we sort of decide, well, maybe we'll collect 600 annotations here. So that's what we were working towards with this. So when we get our 600 annotations, we just go back to the terminal here, stop the server, and then we have all of the annotations stored in the data set that we have here. So from here, we can actually just export the data set if we want into this text-based format. And if we had some other way of training with this, we can just do that as an offline process. But Prodigy also has a built-in training process. If the model is spaCy's named entity recognizer, you can use the recipe out of the box. So the recipe here is just Prodigy ner.batchtrain. And this tends to be more accurate than the model that's been trained in the loop, because it's just a little bit easier to train with all of the examples available, so that you can do the standard deep learning sort of approach of shuffling up the examples and making several passes over them. It's also a lot easier to sort of play with different parameters and things that you always have to basically fiddle with and tune when you're doing these machine learning things. So in this case, we're not going to spend much time tuning these. So this means that there's probably room for improvement in the results that we get here. You can usually get some sort of improvement in tuning the dropout rate, the batch size, some of these other hyperparameters. But for now, let's just focus on the defaults, which usually give okay enough results anyway. So what we write here is we write Prodigy ner.batch train. Then we do this label drugs ner. We start training from the model that we had there, the Ian Core WebLG spaCy model. You can start from a different spaCy model if you want. You can basically save these out, and anything that's a directory or an installed model you can use as the basis of this. And then we set our output directory, drugs-model, the label that we're going to be training, drug, and then we can also set what portion of the data we're going to use as the held out set to produce accuracy statistics, and the batch size that we're going to be training from. And we'll just train for 6 iterations at this point. So in other words, we'll pass over the data 6 times, randomly shuffling it before each pass of the data. Okay, so we execute this command, and it starts printing us some useful information. It tells us, it just sort of reiterates the parameters for us, and also prints the accuracy before the model has done any training. So in this case, of course, the model didn't know anything about this labeled drug, and so of course it gets 0 correct. It also tells us that there's 76 entities where it's not sure whether the entity was correct or not, and so that's going to be the case for things which we rejected. So anything which we hit reject for, it has a label that it says, well, okay, I know that that's not drug. And so in this case, it's assigned those entities a label that's not drug, sure enough, but we don't know whether that's actually correct or not. So we have some unknown entities, or entities where we are not entirely sure whether the annotation that the model has produced is correct or not. And that's a useful thing to track, especially for situations like this where we're training for one label, but there's actually other labels in the model which we are not caring about. But we still may want the performance of the model to be preserved on those examples. So that's going to be printed during training under this ents column. So here we see that after the first epoch of training, we get the loss, which is essentially the area under the curve. This is the measure that the model is optimizing over the training set. And then the number of entities which we know are right according to our annotations, the number of entities which are predicted which we know are wrong according to our annotations, and then finally just the general number of entities which were predicted, which includes all of the non-drug labeled entities which the model is assigning over the data. And then finally the accuracy of the model over this set. So we proceed in this over several passes. The model goes up in accuracy and then starts to go down again as it sort of overfits over this quite small training set. So remember that we're only optimizing over 600 annotations here, which is a very tiny set by the standards of deep learning. But because we do start with some knowledge from the word vectors and the general NER model in spaCy, it's able to learn quite effectively from these, especially since the annotations that we produced have a little bit less redundancy than if you just annotated an unbiased set of data because of the uncertainty sampling that we've done. And so even from this small sample, it's able to achieve an accuracy of 87.5. And again, remember that the data was sampled here in a way that sort of preferred the uncertain cases. And so this accuracy measure may even be an underestimate of its general performance. It may be that when you run the model over general text, a very high proportion of them may be words which are just simply covered. So for instance, every time that we see opiates or heroin in the data, we probably get those instances automatically correct. And so when we run this over text, we may actually be seeing a much higher per entity accuracy than these figures suggest. But again, you can also just continue tuning the accuracy by running this over more text and continuing training. We really only did half an hour or so of work on this, and so with another few hours of work, the accuracy can improve further. Once the model is trained, we have a variety of ways that you can start evaluating it and start seeing whether the accuracy is good enough, and start basically trying it out in different ways. So in addition to sort of more formal evaluations, a very important way to evaluate the model is simply to look at the output. This is sort of the lightweight first check of things. You want to see what it does, right? And this is quite indispensable. No matter how much numeric evaluation you do, you really can't beat actually just looking at the data, because otherwise you don't know whether your numeric evaluation tells you what you think it's telling you. So to make this sort of process easy and quick and also interpretable for you, we have a quick print stream command that essentially just lets you view a nicely formatted output of the model over some running text. So you can stream some text in using the loaders that Prodigy provides and just pass it through the model and give you this handy colored format that you can view on your terminal just to start seeing things. So this is over this data which we reserved as the held out set for checking the accuracy. We've got another set which is drawn from the same distribution. It's the same month but shuffled and set aside, which can be used for final testing at a later date. But at this point, sort of looking through this, the performance in this set, we could then go back and see, okay, we've got some extra terms that we want to add to our model, and some other things which maybe it's missed, or some other things which it's notably getting wrong. And so this is basically the next step of performing these things, is by looking at the data and saying, okay, is the accuracy already, seems like it's good enough, or is there obvious room for improvement? And of course, the next phase of checking that you want to do isn't just looking at the data and isn't just performing numeric evaluation. The next phase is, of course, to take the system and plug it into the next process that you want to do. So in the case of something like this, it would be running the model over some larger stream of text or other sort of text that you wanted to actually start calculating your analyses from. So the next step is obviously being able to actually access the model in a productive way. So, and that doesn't include just piping it through the Prodigy utility. You want to have it as a separate thing that you can actually deploy. And we think that this is actually super important. The work isn't done until you can actually start plugging this forward, and the evaluation isn't done until you can start seeing it in the next context. So we've built utilities that make this super easy. So the NER recipes, like the NER batch train, just produces a model that you can load directly in spaCy. So the usage of these models which you're training with Prodigy is exactly as easy as using the built-in models for spaCy, which people already have in production in hundreds of companies, some of them quite large. So all we need to do here is write import spaCy, and then we can do nlp equals spaCy.load with the path to our model, drugs model. Then we can do doc equals nlp using this as a callable object, and just give it this example, fentanyl is dangerous. And then from this we can see that the entities, which we can access via this doc.ents attribute, gives us indeed this the correct result. We get fentanyl noted as a drug. If you're already using Prodigy, I hope this has given you some extra insight into how the named entity annotation recipes work, and also some ideas for your own projects of what you can do with these capabilities and how quickly you can train a new model for to recognize a new phrase type, even phrase types which aren't normally considered as named entities, like that don't center around proper nouns. If you haven't seen Prodigy yet, all of the information can be found in the video description. You can find this on our website. There's already a lot of documentation there and other videos that you can see about how the tool works. The main thing to keep in mind that people seem to be surprised by is that it's a downloadable tool. It's not a cloud service, and none of the data has to leave your service. And also the licenses to Prodigy are lifetime, so it's not something that's attached to an ongoing fee from us, and you're not going to be dependent on our services in any way. So it's kind of like the more old school model where that Adobe had, where you basically just pay a one-time fee and get a professional tool. And we think that that's a pretty productive way to work that really basically sets us on the same side and things, and doesn't lead us to continue trying to trick you in some way to make you dependent on us and things. We think that this is basically a nice way to keep working. And so we hope you'll check out Prodigy and get some ideas for what you can do. Thanks.